Today on How It's Made. Ceramic fireplaces. Synthetic corks. And parking garage floor slabs. The first fireplaces were strictly functional, for heating the home, cooking meals, and warming water for bathing. Over time, fireplaces appeared in other rooms of the house and acquired aesthetic features such as wood, stone, or tile work. This ceramic fireplace is a heritage model, inspired by fireplaces of the late 19th and early 20th century. Certain tiles are exact replicas of originals. At the ceramic factory, they mix water with clay, feldspar, and silica in a pug mill. Together, these formulate a clay blend. Once the mix is the right consistency, the operator presses a button, and the mill switches to extrusion mode. This forces the clay blend through a mantle-shaped die and produces a 10 to 15-inch long extruded mantelpiece. They trim the piece with a cutting wire to the precise length required. They use this extrusion method for making longer pieces. If they need shorter ones, they often cast them individually in a mold. When casting, they add significantly more water to the clay blend to produce a liquid clay called slip. They pour the slip into a plaster mold. The porous plaster gradually absorbs most of the water, leaving a layer of clay about 6 millimeters thick on the walls of the mantle-shaped cavity. After a few hours, they pour out the excess slip and open the mold to extract the cast mantelpiece. Once the clay becomes firm enough to handle, they carefully trim off the excess around the opening in the mold. Then they gently smooth down the seam along the junction between the two halves of the mold. On the opposite side of the pour hole, they cut out a matching hole. This will help the clay dry faster by enabling air to flow through the inside of the piece. To compensate for shrinkage, the molds and extrusion dies are designed 11% larger than the size of the finished piece. Clay shrinks as it dries. To make the fireplace's ceramic tiles, they produce a rubber mold of 2 adjoining tiles and place it inside a metal casing. They also include a release system to help with extraction. They fill the casing with an exceptionally strong type of plaster. It sets in about half an hour, taking on the shape of the rubber mold. This plaster casting is the die they'll now use to produce the tiles. They mount the die on what's known as a ram press, because it literally rams a block of clay in the die and compresses it with 30 tons of pressure. The tile die is also 11% larger than the final size to compensate for shrinkage during drying and firing. They remove excess clay and send it back to the pug mill to be recycled. Then they position a board under the die and activate the release system, which extracts the clay with a blast of compressed air. They trim off the excess clay. Once dry, the tiles and mantelpieces are ready to be glazed. Glaze is a chemical formula containing finely ground silica, combined with different combinations of metallic elements to produce specific colors. They use a spray gun to apply glaze to the mantles and a tube tip applicator to glaze the tiles. The tile design has raised borders between its components. These are called Cuenca lines. They prevent the different color glazes from flowing into each other. The glazed mantelpiece and tiles now go into a gas-fired kiln for 12 to 14 hours. The high temperature, 2100 degrees Fahrenheit, triggers chemical reactions which harden and strengthen the pieces. The clay's mineral composition transforms into a completely new configuration of crystals and glass. As for the glaze, its precise formulation of metallic elements produces a specific color, and the silica melts into a glass surface. The ceramics are now smooth and shiny, and ready to transform an otherwise ordinary fireplace into a work of art. Many winemakers choose to seal their bottles with synthetic closures instead of natural cork from tree bark. This prevents cork taint, which happens when natural cork gets contaminated by the TCA molecule. Cork taint is completely harmless to humans, but spoils the taste of the wine. This engineered cork is entirely synthetic and therefore resistant to TCA contamination. It's made of a food-grade polyethylene foam core encased in elasticized polymer skin. Both materials contract to squeeze inside the bottleneck, but then regain their original shape to seal the opening. To make the foam core, they mix talc with pellets of low-density polyethylene, a pliable type of plastic. Then they add pellets of dark brown and beige colorant to mimic the wood grain look of natural cork. For each customer's order of corks, a computerized system automatically releases the right amount of each ingredient into an industrial blender. The blender feeds a specially designed dual extrusion machine. The machine melts the foam mix to a liquid state, then injects carbon dioxide. This produces bubbles which create the cellular structure of the foam. The liquid foam enters the machine's horizontal extruder, while elasticized polymer enters the machine's angled extruder. Both extruders squeeze their materials through the same shaping die, which outputs a continuous rod of skin-encased foam. The foam core immediately expands. The elastic skin stretches with it. A water bath cools the rod, halting this expansion at a specific diameter. Then, an underwater ultrasonic gauge measures the thickness of the outer skin to make sure it meets specifications. The rod exits the water bath and continues cooling and shrinking as it drip dries. A laser gauge then verifies that the rod is perfectly round and measures a specific diameter by this point. When any of the measuring gauges detects an area that doesn't meet specifications, that part of the rod is flagged in the system and is discarded at the end of the production line. The rod now enters a final cooling phase. It travels in several loops past nozzles spraying cold water. As the rod cools, it shrinks to its final size, a diameter of between 22 and 23 millimeters. It's designed to fit snugly inside the standard 18.5 millimeter bottle opening. They had to calculate exactly how wide to extrude the rod, so that after expansion, then shrinkage, it would end up at this precise diameter. The rod now enters a cutter. The blade is so sharp that a safety cover is mandatory. It's removed here only for the camera. The winery placing the order specifies the cork length. Air jets automatically blow off any corks cut from areas the measuring gauges flagged as being problematic. The cutter slices about 10 standard length corks per second. All the good corks land on the conveyor belt and travel to the end of the line, where computer sensors count them as they drop into a collection bin. Additional machines print on the winery's name and logo and lubricate the surface with silicone, so the corks will glide in and out of the bottle with ease. The factory's on-site lab tests samples from every order. Sensory specialists sniff each cork and compare it to a control sample. There must be no discernible odor that might affect the aroma or flavor of the wine. If there is, the entire order of corks fails inspection. While natural cork is designed by Mother Nature, a synthetic cork manufacturer can engineer the closure to fit more or less snugly, according to the amount of air the particular wine needs to develop correctly. Multi-tiered parking garages have become an urban phenomenon. With each floor added to the garage, the number of parking spaces increases. In crowded cities where land is limited, garages like these are a necessity. They build parking garages one concrete slab at a time. These slabs are known as double T's because the two support beams are in a double T configuration. Double T's are often factory-made and transported to the construction site later. They are designed to hold up under very heavy loads. They make these slabs outdoors. Wind blows dirt onto the mold, so they sweep it clean. This mold is about 500 feet long and will be used to make several slabs. They spray an oil-based release agent onto it. The release agent will allow the slabs to be easily extracted when complete, preventing cracking. They spread it more evenly using mops. This release agent bonds to the metal quickly and won't wash off easily if it happens to rain. They're now ready to assemble the floor slab's elaborate support structure. They prop up the ends of each slab with galvanized steel stirrups. They place L-shaped bearing plates in strategic locations along the mold. Then they insert wooden blocks in the mold. These blocks will form notches in the cast concrete that will be used to join the slabs during construction. Next, workers thread high-strength steel cables called tendons throughout the beam sections of the mold. They pull the ends through holes to the outside of the mold and clamp them. A worker tucks another wood block between two tendons to complete the notch part of the mold and hold the tendons in place. The team threads more tendons throughout the mold, weaving a strategic support structure. To separate each cast slab, they insert wooden dividers with slots that accommodate the tendons. They adjust the location of each of the stirrups so that they sit at a specific spot near the dividers. With the final tendons in place, they bring in a hydraulic jack. The worker attaches it to one of the protruding steel tendons. He activates the jack, and it pulls the tendon until it's stretched tight like a rubber band. He pulls the rest of the tendons with the jack and checks the tension to confirm that it's exactly the same for each one. Pulled tight and later released, the cables will hold the concrete under compression, adding strength to it. Without it, the concrete slabs would never be able to support the weight of many vehicles. The next worker ties a plastic bracket to the stirrups to set them at the right height. He inserts metal mesh into the mold where each slab will end. This will help disperse some of the concentrated bearing stresses. He stabilizes the mesh and reinforces it with this support structure. The team places plastic pockets along the tops of the beam sections of the mold. These pockets will be used to chain the slab to the truck during transport. They'll also act as entry points for electrical wiring and hold controls for parking space counting equipment. Coming up next, the deck section gets plenty of extra support, and then it's set in concrete. The average car weighs well over 2,000 pounds, so each parking garage floor must hold up many times that weight. Double T concrete slabs make this possible. Each slab has 2 reinforcing beams, and each beam has a tense steel skeleton that compresses the concrete, making it stronger. With the steel tendons stretched through the beam parts of the mold, workers now lay metal mesh across the deck. This mesh is known as welded wire fabric, and it will reinforce the surface of the parking slab. They tie the welded wire together for full coverage across the deck. They use plastic clips to prop up the wire so that when they pour the concrete, it will envelop both sides. They insert handles that will protrude from the ends of the completed slab to allow it to be lifted for transport and installation. There are 4 double handles in each parking floor slab. They enmesh the prongs of weld plates in the steel grid. The plates are strategically positioned for the welding of the slab to other pieces of concrete. All the prep work is finally done, and they pour the concrete. The concrete flows into the beam sections of the mold first, and then workers spread the overflow across the deck. This is a high-performance formula that's known in the industry as self-consolidating concrete. It flows evenly into tight spaces and compacts better without the need for much vibrating. This leveler vibrates the surface of the concrete only slightly as it evens it out. They then rake the surface of the slab to allow another layer of concrete to adhere to it later during construction. They now insert arced metal bars into slots on the sides of the mold to form a ribbed framework down the length of it. This serves as a support structure for a tent. They unroll the tarp from a huge spool and drape it over the ribbing. They secure the canvas to the sides of the mold with hooks. The tent will shelter the concrete from the wind and rain as it cures. Along with an additional plastic layer, it will contain the hot and humid conditions created inside. The heat accelerates the curing of the concrete, and the humidity prevents cracking. The cure takes 16 hours, and then they roll up the tarp. Using a torch, they cut the steel tendons and place the concrete under compression. The cuts also separate the slabs. A driver now parks his crane over one of the slabs. Workers attach the hooks of the crane to the protruding handles at the ends of the slab. They signal the crane operator and he activates the lift. Thanks to the release agent applied earlier, the concrete slab easily dislodges from the mold. It's a heavy load. Each slab weighs 40,000 pounds. The crane sets it down, and the team inspects the slab for defects. Satisfied that the slab is free of flaws, a worker trims the protruding steel tendons flush to the concrete. Another worker spreads a concrete-like paste on the exposed ends of the severed steel to seal it from the elements. Then, a worker glues rubber pads to the bearing plates. They'll act as cushions when the slab sits on another concrete beam. He wraps some tape around them while the adhesive sets. This parking garage floor slab is now ready to join the rest. Side by side, the slabs will form one large parking surface to create even more spaces. If you have any comments about the show, or if you'd like to suggest topics for future shows, drop us a line at sciencechannel.com/howitsmade.